Okay, so we have a pipe here and the water's flowing through it from A to B. There's a small radius at A and a big radius at B, and my question to you is, when we let it flow like this, is the velocity of the fluid faster at A, or is it faster at B, or are they going the same speeds at A and B? Okay, so it's going faster at A. So why is the velocity at A bigger and the velocity at B smaller? Well, it's because the flow rate Q is equal to a constant. And in a tube like this, where there aren't any holes so no liquid leaks out, Q, the flow rate, is equal to the area of the tube at any point times the velocity of the fluid at any point. So basically what that means is that A here, the flow rate Q would be the area at A, sorry, we have two A's there, times the velocity at A. And then since we know that Q is a constant, that has to be equal to the area at B times the velocity at B. And since it's pretty clear that the area at B is bigger, in order for that to equal the area at A times the velocity at A, the velocity at B would have to be smaller. Okay, so now my question is, while it's going through the tube, is the pressure greater at A, pressure greater at B, or is the pressure the same at both? Okay, so why in the world would the pressure at A be less than the pressure at B? Well, this is a job for Bernoulli's equation, which says that the pressure at any point plus 1/2 the density of the fluid times the velocity of the fluid at that point squared plus the density times g times the height of the fluid is equal to a constant as we go through the tube. So what that means is that we can equate this quantity at A to the quantity at B, and they have to be the same because this quantity is a constant. So basically what I'm saying is that the pressure at A plus 1/2 the density, which is the same everywhere, times the velocity at A squared, plus the density times g times the height at A is equal to the pressure at B plus 1/2 the density times the velocity at B squared plus density g height at B. And note that the height at B and the height at A are about the same, so we can just cross those off. And we already figured out that the velocity at A is going to be bigger than the velocity at B because the radius is smaller at A. So since this is big and this is going to be smaller than that, for the two sides to be equal, we know that the pressure at B has to be bigger than the pressure at A. Okay, so here's the situation. We got some water going in a pipe. It's the same radius all along the pipe, but it goes down here from A to B, kind of like this. And my question to you is it going faster at A or is it going faster at B? So the velocity at A is going to be exactly the same as the velocity at B. So why is that? Well, it's just like before. Q equals a constant. So the area times the velocity of the fluid is a constant. And so since we know that the area of the tube doesn't change, the velocity also doesn't change when you go from A to B. Now my second question to you is the pressure greater at A or is it greater at B? Okay, so why is the pressure at B greater than the pressure at A? Another job for Bernoulli, which tells us that the pressure at A plus 1/2 rho velocity at A squared plus rho g height at A, which is important here, is equal to all that stuff at B. Density at B plus 1/2 rho VB squared plus rho g height at B. Okay, so here we know that the velocity at B and the velocity at A are the same, so we can cross those out. And we know that the height at B is going to be less than the height at A. So this is bigger, this is smaller. And so for the two sides to equal, we know that the pressure at B has to be bigger and the pressure at A has to be smaller. Alright, so we're going to have a race between these two air bubbles which are in water. We have a small one and a big one, and they're both approximately spheres. So predict which one will make it to the top first. Okay, on your mark, get set, go. And the big bubble wins.
Woo!
So why did the small bubble sadly lose the race and the big bubble reigned victorious? Well, let's look at the forces on, say, the big bubble. So there's a mass of air in this bubble. So because the air has mass, we have the gravitational force, mass of air, times gravity going down. And then we also, since we're moving up, it's moving up, there must be an upward force. And what force is that? Yeah, you got it. It's the buoyant force, which is just equal to, as you know, the density of water times the volume of water that the bubble displaced times g. Okay, so how do we know that that's going to be bigger than the gravitational force? Well, we know that this mass of air can just be written as the density of air times that same volume. And remember that this is a negative number. We can write it, and we also put the gravity there. So this is the downward force, and then this is the upward force. So basically we could write this by adding these two together as the volume times g times the density of water minus the density of air. And we could actually do the same thing for the small bubble, but the only difference for the small bubble is that the volume is going to be smaller. So what that means is that we'll have a little volume times gravity times the density of water minus the density of air over here. And so what that means is that we have a smaller positive number. That means a smaller force upward, and this bubble has a bigger force upward, and so it's going to be pushed up more quickly by that bigger force, and it will reign victorious. So imagine putting this straw in this bucket of water. So originally the surface of the water is completely flat all the way across, but if we look closely in the straw, is the surface flat? Does it bulge down? Or does it bulge up? So it bulges down. Now why is that? So the water bulges down like this due to both cohesion and adhesion, because cohesion is a desire for the molecules in the water to want to stick to each other, and adhesion is the desire for the water molecules to want to stick to the side. Now, the adhesion is stronger, so the water molecules more strongly want to stick to the side. And if they bulge like this, then they're able to stick to the side more than they are able to stick to each other. Now, we know it's bulging down, but does it stay where it is? Does it start moving down? Or does the surface of the water start moving up? The water level actually starts moving up. So why does the water level go from here and then move up? Well, the reason is because if we're just here at the surface, when we're not in the tube, the atmosphere is pushing down with the pressure of 1 atmosphere. And then right below the surface of the water actually also has a pressure of 1 atmosphere up. But then if we go over here and look inside, there's 1 atmosphere up here, but then down here, there isn't just 1 atmosphere of pressure on the bottom. There's also another force that we're not considering on the surface here. What is it? Yeah, you guessed it. It's surface tension. So surface tension is pulling up on the water here in the tube, and then that means we have the surface of the water moving up in the tube.